Physics is the fundamental driver of our universe.
And it exists in the world around us.
My name is Doug.
My name's Hussein.
And we're here to teach you about momentum and impulse. Let's get into it.
But before we begin, let's start with a little review.
Before we get into the fun stuff, we'll briefly be going over some of the key concepts such as forces, momentum, Newton's laws, impulse, and elastic and inelastic conditions. Let's start out by going over some of the important equations. Take note of them as you will need these for the review questions that will follow. The first one doesn't get any more fundamental. Force equals mass times acceleration. Easy enough. But how about the second one? That's right. Momentum equals mass times velocity. And last but not least, impulse equals force times the change in time, which also happens to be the change in momentum. Now let's look over two key collision types. The first one is a perfectly inelastic collision. A perfectly inelastic collision is a type of collision in which colliding objects stick together after the collision and move as a single object. In this situation, kinetic energy is not conserved, as some of the initial kinetic energy is lost and converted into other forms of energy such as sound, friction, and deformation. The second type is a perfectly elastic collision. A perfectly elastic collision is a type of collision in which colliding objects bounce off each other with no loss of kinetic energy. In other words, the total kinetic energy before and after the collision remain the same. Perfectly elastic collisions are theoretical and idealized because in real life, some of the kinetic energy is always lost due to factors such as friction or deformation of the objects. The collision types won't be asked about in the following questions, but will be good to know if you want to learn more about the conservation of momentum. Let's get into the review. Let me set the scene. You're traveling down a beautiful and scenic highway in your freshly washed car, when all of a sudden you rapidly start approaching a bug. Oh man, you hit the bug and you splattered all over what used to be a crystal clear windshield. During the collision, how did the force on the bug compare to the force on the car? Is it A, greater than, B, equal to, or C, less than? Take a moment to pause the video and figure it out. If you got B, equal to, you would be correct. Let's move on to the next question. Given that the car weighs 1,300 kilograms and is traveling at 36 kilometers per hour, what is the momentum of the car? Is it A, 3,900 kilogram meters per second, B, 3,600 kilogram meters per second, or C, 13,000 kilogram meters per second? Take your time to find the correct answer. I will even throw a hint up on the screen. If you answered C, 13,000 kilogram meters per second, you would be correct. Now what about the bug? What is the momentum of the bug given that it weighs 1 gram and travels at 3 meters per second? Is it A, 0.0001 kilogram meters per second, B, 0.3333 kilogram meters per second, or C, 0.003 kilogram meters per second? Pause the video and find the right answer. If you answered C, 0.003 kilogram meters per second, you would be correct. On to the last question. Final question. So, how does the impulse on the bug compare to the impulse on the car? Is it A, greater than, B, less than, or C, equal to? If you answered C, equal to, you would be correct. How did you guys do? Now, let's look at an overview of what we reviewed. In summary, the force of the bug on the car and the force of the car on the bug are equal because of Newton's third law. And since impulse is a force times the change in time, The impulse of the car on the bug and the bug on the car are also equal. Finally, since force is equal to mass times the acceleration, we can conclude that the mass of the car times the acceleration of the car is equal to the mass of the bug times the acceleration of the bug. However, since the mass of the car is so large, it means that the acceleration for the car will be very small. And unfortunately for the bug, since its mass is very small, the huge acceleration is what ultimately results in it getting squashed. Now that we're done with the review, it's time for the fun stuff. This is Hussein. He's been boxing for 5 years and he's going to show us what he can do to a punching bag.
The MMA gloves might pack a punch, and they certainly are big.
But these are the big guns.
We can see that these gloves certainly do pack a punch, and no one exemplifies this better than this man right here. Now let's take a look at the great Muhammad Ali. Ali was known for his knowledge in boxing. What could you say? He was a very smart individual, and boxing in itself is filled with many lessons in physics. Now here we have standing is Muhammad Ali, and also we have his opponent, George Foreman, as they both compete for the Boxing World Heavyweight Championship. Now, let's see how this match goes. We see Ali going in for the punch. Foreman doesn't really know what to do, and he just falls over. Ladies and gentlemen, there is no need for a count. Not at all. Because this is what we call a KO. And we have our winner and new champion, Muhammad Ali. Now, you must be wondering, how did he do this so easily? Well, to answer that question, we have to take a bit of a closer look. Along with that, though, to fully understand this, we must answer a few quick questions. The first of which being, if Ali throws two purely horizontal jabs at Foreman, both with a force of 300 newtons, the first having a contact time of 0.5 seconds and the second a contact time of 0.8 seconds, which punch has a higher impulse? Is it the 0.5 second punch, the 0.8 second punch, or do both punches have the same exact impulse? Well, let's take a moment to figure out this answer. In reality, the 0.8 second punch has a higher impulse. Now, let's see how this looks in demonstration. We see that the punch makes contact, it hurts, but not as bad as it could have. You must be wondering, why is that? Well, to answer that question, give us a moment. This is due to something called riding the punch. Now, you must be wondering, what is that? Could it be something like this? Moving around? Whoa! Well, probably not, right? In reality, riding the punch is a very smart technique many boxers use, but Ali was known for using. What happens is when a boxer throws a punch at his opponent, they move back with the punch. This increases the contact time. However, since the impulse does not change, the force must decrease in the punch. And you can see in here that force and time are inversely proportional, so if time increases, the force must decrease. Let's look at an example of this. If we have a match against George Foreman with Ali, and Ali rides the punch on two different occasions, assuming both punches have the same impulse, I ask which punch has a lower force. Would it be the first punch that Ali rides for 6 seconds, the second punch that Ali rides for 3 seconds, or the most obvious answer, that Doug would come in and KO everyone and just walk out of the ring and leave? Let's take a moment to answer this question. In reality, what would happen is the first punch would have the lower force. So, when Ali really gets hit, it doesn't really hurt that bad because the contact time was a lot higher. Finally, let's summarize what we learned today. We know that impulse is the effect of a force of an object over a period of time. This can be quantified as the change in momentum or the product of a force over a time interval. We also learned how this could be used in real life. Specifically, in our example, we used boxing and how riding the punch and how impulse can change how much damage is inflicted on an opponent. The conclusion we came to is that when riding the punch, the impulse stays the same. This means that we have a longer time interval, thus we net a lower impact of force.
We just explained how physics can give you an edge in boxing.
Now it's your turn to think about where physics applies in your life.
Thanks for watching.